Hello everybody. I was lecturing to my undergraduate organic chemistry class recently on the Birch Reduction, and a colleague was sitting in, and afterwards he said to me, Kevin, I don't know if I like this mixing up of fishhook and double-headed arrows, like this. Okay, let's see how that works for the Birch Reduction, because it is a little bit tricky to push the arrows around. How would I do it? Can I do it with fishhook arrows and double-headed arrows? Or am I from the Galapagos Islands of chemical weirdness? Let's see. If we take sodium or lithium or calcium and drop it into liquid ammonia, we see a vivid blue inky color, like an octopus is dying in the solution. It's not an octopus and it's not a death, that's solvated electrons, and they're very powerful reducing agent. One of those electrons could add to an aromatic like benzene, and I choose to show this with one fishhook arrow and one double-headed arrow. Of course, you can show it with 3 fishhook arrows if you want to, and the only difference is you change the position of the radical and the anion, and therefore you probably have to say, well, the electron is attacking here and not there. It doesn't make any difference, at least not in the case of benzene. Okay, so the electron attacks benzene. It's a neutral benzene plus a negative electron. You get a radical anion. And the radical and the anion, if I just push one arrow, they're adjacent to each other. We don't like them. So let's resonate them apart. And now we've got the radical and the anion as far as they possibly can be. It's a bias in the resonance structures. And that radical anion can be protonated by an alcohol. In the Birch reduction, we usually add alcohols to give us a relative source of acid. So we add a proton to a radical anion, we get a neutral species, which is still a radical. That radical has a limited lifetime, but fortunately there's lots of electrons. One electron adds to the radical, and it gives us an honest-to-goodness anion. That anion can be protonated once more and will generate the product, a 1,4-cyclohexadiene. In other words, 2 non-conjugated double bonds. The Birch reduction then. Neutral, radical anion, radical, anion, product. Got it? Sometimes you will see this. 2 negative charges in conjugation with each other in an 8-pi electron system. People have taken different heterocycles and tried to reduce them and perhaps added different electrophile. Tim Donahue in the UK took this furan derivative and did a liquid ammonia sodium reduction. The electron could add to any of the carbons really, but I've drawn it to account for the product that's formed. So it puts the radical stabilized by resonance and the anion on the other side of the furan. That radical anion can be protonated. They didn't add an alcohol, it's a less acidic medium, but it will get protonated. And when it does, we generate a radical. There are more electrons in solution. One of them adds to our radical. It generates an honest-to-goodness anion. And then instead of adding a proton, this anion is stabilized, remember? We can add an electrophile. How about methyl iodide? When we add methyl iodide, we get this substituted, reduced furan ring. And you can go on and do interesting things with that. I'll leave you with another mechanism. Figure this one out for yourself. You have to recall, Birch reduction of methoxybenzene gives an enol ether. In other words, the methoxy is substituted on the alkene. How do you account for reduction of the benzene ring and the benzylic CO, then ozonolysis giving us this product? Write it down on a piece of paper. It's kind of useful actually to use an aromatic ring to form a 1,3-dicarbonyl compound. So do you like it? Tell me. Thank you.